Hello math fans. I'm going to make a video about this so-called Basel problem solved by Leonard Euler. This is a problem I've thought about a lot for a long time. Again, I've taught at the University of Washington for 20 years. When I was a grad student in undergrad, this is one of the problems that caught my attention and drew me into math. And I've wasted a lot of brain cells on it. And I hope in making this video to put it down. Super interesting question. Lots of things stem from it. And I have too many notebooks full of trying to solve unsolved problems that I think I need to stop. And I haven't thought about it for years, but as I pick up these old notebooks, I'm kind of drawn back into it. And I want to put it away. And I'll feel better if I post this video and maybe this introduces some of my students to this problem. And maybe some of you can make some progress. And then I would feel better. I know that if I post a video like this, there's others that know a lot more than me. They're probably going to find this video and tell me in the comments that they know a lot more than me, and they're absolutely right. But anyways, I just want to give you Euler's proof because it was so enthralling and show you why it caught me. And then I'll say a little bit about Euler and talk about some of the problems that got me stuck. So this problem was posed in 1650. It was solved by Euler when he was 28. And what caught my attention is he was a strong mathematician. I would arguably one of the greatest of all time, or the greatest, in terms of his accomplishments he made across many fields. It wasn't just math. Well recognized as one of the most prolific scientists of all time. But anyways, this is what really really shot him to being the best of his time when he solved this problem. So it has some interesting history because many people tried to solve it. This was after Isaac Newton and everything. And he proved that the following, which they already knew was this decimal, the sum of the inverse squares, equals pi squared over 6. And it's so unusual. We have a bunch of integers here. And once he proved this, you could numerically check it really far out. There was some rigor that was needed in his argument that was filled in later. But I'm just going to give you his original proof, and I've never done it for anybody. And so I'm just going to do it now, and hopefully I remember. But his proof was so short. And I know there's better videos on things like this. So I'll talk about the proof, and then I'll talk about some history. So these are very important functions. This is called the Riemann Zeta function at 2, and there's a 2 here. Values of this function come up in relation to studying prime numbers and number facts, and there's this Riemann hypothesis, which is one of the most famous unsolved math problems related to this function, but I'm not going there. I had enough trouble here. So anyways, this was... I don't know how Euler came to this. He was from Basel. He was a Swiss mathematician. That's why it's named this. But he studied a lot of infinite series, infinite products. And it was well known that you could write the Taylor series for this function as follows. And my calculus students will do this in Math 126. It has the following pattern. It's actually part of a much bigger series. 2n plus 1, bigger discussion x to the 2n plus 1. It has all these odd numbers. Looks like this. 1 over 3 factorial x to the 3, 1 over 5 factorial x to the 5. And this approaches it and gets closer and closer. That's why we can put this equal sign here. So I was going to show you some visuals of this, just briefly. So here's sine of x. Here's the Taylor series. So in Math 126, you're going to talk about how if you just do the line x, you just get this line, which is the first approximation at 0. And then here's ultimately the third approximation, the third power. And it's really cool. It like hugs the function. And you can do that for any function. So Taylor series is really valuable because it gives you a way to turn any function into a polynomial. And it approaches it. And it doesn't just work for that, it works for anyone, just by taking the derivatives. So it's really valuable to be able to turn things into polynomials. Okay. So that's a big area of math that everybody who studies calculus eventually studies. So he knew this fact. And people at the time knew this fact. What was interesting, and I imagine he thought, I imagine this is how he came to it. But, if you have like a polynomial, x minus 2, x minus 3, and you set it equal to 0, you say the roots are 2 and 3. And even if it's written in an expanded form, what would this be? Minus 5x plus 6. You can factor it if you know the roots are 2 and 3. Okay, so he said, well, I know that the roots of sine are. Now, it's not a polynomial, so this is the part that would need a lot of justification. But it has a lot of roots. This is a pretty short proof, so stick with me. Proof I should put in quotes. But where are those roots? Most students would know that it's at 0 and pi and 2 pi and 3 pi and 4 pi. And there's also negative pi, and there's a lot of them. So what Euler tried to do is factor this. And I imagine, I don't know if his first attempt was to write all of these, x minus pi and x plus pi and x minus 2 pi. Maybe that was his first attempt. Probably not, because he's so prolific. But it turns out this does not approach anything. So he wrote it a different way, basically by like factoring out the 2 and the 3. So you wouldn't think about this here. No one ever writes it this way. But if you factored out the 2 and factored out the 3, it would still have the same roots. And so that's what he did. He didn't write it this way. He wrote it this way. So x for the 0, and then he wrote 1 minus x over pi. And this is actually going somewhere. So he did the plus and the minus, and then he wrote 1 minus x over 2 pi. Okay. And then he wrote 1 plus x over 2 pi. And so on forever. And the problem is this doesn't really approach, but he did something clever. He put these two together. It's a difference of squares. So he did 1 minus x squared pi squared. And I am remembering. Good. 1 minus x squared. I mean, I've had these proofs in my head for 20 years. I should be able to recall them. X squared, 3 squared pi squared. A good mathematician probably can recall this without thinking, but I'm not a good mathematician. Okay, so anyways, Euler said, well, what if these are the same? Now that's the part that requires some proof. I did make a visual of that. Infinite products are a much harder game to play. They don't approach in the same way. Taylor's series, you can see, get closer and closer in an interval. But this one usually has these gaps. And so it doesn't quite approach the same way. But it's really pretty how it does. You keep going out. So it does approach. And this was the clever idea that Euler had. Okay, so why is this clever? Or what was the idea he had? He said, well, we've now thought of something in two different ways. And this is often something that happens in math, is looking at something two different ways leads to an interesting result. So we have two dramatically different representations of sine. And so the next step was, he said, well, what if these two things are equal? And he divided both sides by x. So he wrote 1 minus x squared over pi squared, 1 minus x squared over 2 squared pi squared, 1 minus x squared over 3 squared pi squared, and so on, equals this thing. And maybe I'll just write it up here. We're going to divide everything by x, so it's going to become 1 over 3 factorial x squared, and we're almost there. X to the 5th. Okay. So then he made the following really clever observation. You might notice these squares that are here. He said, what if we could FOIL this out? Now, it's hard to FOIL this out because you'd have all sorts of things. You could do this times this and then times that. There's an infinite number of foiling. He didn't actually foil the whole thing out. He asked, well, what's the smallest thing you're going to get? Well, if you multiply all the ones, you're going to get a 1. And that's the only way you can get a constant. So if you multiply all the ones out to infinity, and this is the rigor that had to be filled in later, that sort of doesn't satisfy, the precise rigor of mathematics, but he filled it in later. Anyways, how can you get x squared? Now, if you think about it, if you do x squared times x squared, you're going to get x to the 4th. So the only way you can get x squared is if you do this one with all the other ones. That would be one way to do it. So let's write that out. That would be this. The next square you're going to get is this one with all the other ones. So you're also going to get this. Let's zoom out a little bit. The next one you're going to get is x squared over 3 squared pi squared when you do this one times all the ones, and so on. And that's going to be all the x squareds. It's going to be infinite, and then you're going to start to get the x to the 4th and the x to the 6th and all the other stuff. So the observation was this. Well, let's factor out that x squared. And what do you get? You get negative 1 over pi squared minus 1 over 2 squared pi squared minus 1 over 3 squared pi squared, and so on. And here was this big observation, is that this, the number next to x squared here, should be the same as the number next to x squared in the Taylor series expansion. And so what he did is he said, from that we can say that negative 1 over, as long as all of this is valid, 1 over 2 squared pi squared minus 1 over 3 squared pi squared, and you keep going, is equal to negative 1 over 6, which is what this is. And then he multiplied both sides by negative pi squared, and he got 1 plus 1 over 2 squared plus 1 over 3 squared is equal to pi squared over 6, which is really miraculous. So it's using special properties of sine. So buried in there was these sums of squares. And again, that took 80 years to prove. It was remarkable when he proved it. It shot him to kind of superstardom in math. I think he got the attention of some Prussian or Russian royalty. Anyways, so I always found that really interesting. Briefly about Euler, but he was born in the 1700s, so this was after Isaac Newton. This is a portrait of him, kind of famous portrait. I was born in Basel, Switzerland. Most prolific mathematician of all time. A whole bunch of things are named after him, so I just grabbed a couple facts, if you didn't know this. It said he popularized the symbol pi. He popularized using I for the imaginary number. Popularized using the Greek symbol sigma, popularized the change symbol delta. He studied exponentials and logarithms, and later the E comes from him. That's a lot of the constants we use. So it's him that you have to blame. I read, maybe I didn't put it in here, that he was well liked. He wasn't, he's approachable. Wasn't quite like many geniuses in math history. He got married. He had 13 children. But what I remember the most in reading his history, besides the fact that there's so many results from his that I've used, he studied things in such a broad range of topics. Astronomy, physics, engineering, mathematics. It's so many things. It's just unbelievable. But people at that time did study more. But his eyesight got worse, and he hurt one of his eyes, which has become I hurt one of my eyes last year. It's going to be okay, but I can't quite see as well out of it. So I've thought about Euler a little more. But he basically couldn't see out of one eye. And I thought it was funny. He says, now I will have fewer distractions. I mean, what a good-humored soul. The other eye started to get bad. And basically, by the time it said he was, in 1966, he could hardly see out of either eye. And what's remarkable to me is then, 9 years later, he still was publishing a paper a week using scribes. I don't understand that. I don't know how he did mathematics that way. It's one of the most remarkable things I've read about the history of mathematicians. Anyways, the day he died, he was still doing research. So, of all the mathematicians I've read about, I always kind of thought, oh man, what a guy. What all the things he did. I didn't know him. He definitely drew me in reading those stories. So back to this question. So if you read on, you find out that this proof, sort of manipulating what he did, you can get all the even powers. And you might start to see that, because if I'd extended this out, there would have been a 4 and a 6. And if you organize it a little better, you can actually prove a general formula. These are the Bernoulli numbers, which again, I don't remember that much about, but there's these patterns. What you should notice is that all the odd powers got skipped. And that's the thing that drew my attention. So the sum of the inverse cubes essentially is an unsolved problem if the question is, what is a closed form for it? You might say, is it pi to the third? Nope, no one's been successfully able to prove that. I think some people have talked about, if it was a fraction times pi to the third, the fraction would have to be astronomical, because it's been tested way out. I think Euler conjectured that it involved a pi and a log of some sort, but was unable to prove it. He proved a whole bunch of stuff about this. He wasn't even able to prove that this was an irrational number. That didn't happen until 1979 or 78, when this mathematician last name Apery proved this. I don't know if I'm saying it right. So this is called Apery's constant. The Riemann zeta function at odd values is something I've wasted a lot of time on, and I hope to never fall into that pit again. But I wanted to pull up something about it. So here's just the Wikipedia article about the Riemann zeta function at 3. It says it does come up in some applications, and it was proved in 1978 that it's irrational. Turns out very little is known about these values. Now, when I say little is known, they can be approximated, but giving a closed form or proving they're irrational is hard. No one's able to get a good handle on them. Now, all sorts of identities have been proven about them and things they're equivalent to, because people have tried to prove these things. So they wanted to be like Euler, like I wanted to be. And so I have notebooks full of identities I've tried to prove and unsuccessfully. It was a paper I started to write to try about zeta function identities, but I realized it wasn't really that significant. Didn't publish it. So don't fall into that pit like I did. But I hope that was interesting to you. I find the history kind of especially interesting. So there you go. There's this particular fact that the sum of the inverse squares is this. If you're worried, just briefly, I looked it up. This comes up in the study of prime numbers. So if you flip this number represents the probability that two random numbers have a factor in common. So if you take two really large numbers, do they have a factor in common? For example, if you take like 33 and 102, they're both divisible by 3. Watch my other video if you didn't know how I knew that so quickly. So there's about a 60% chance. So these numbers come up in a lot of things like that. That's why the Riemann zeta function is so important. All right, hope you found that interesting. I think after this, I'm going to switch back to talking about things that will help my students and some other things. But I just wanted to make that mostly for myself so that I will not touch this again. Maybe some of you will prove something about the Riemann zeta function at 3 or 5 or 7. But don't invite me to the party. I want to know you did it. But keep me away, because these sorts of expressions and manipulations, I'm always drawn into them, but they're a big time sink. All right. Thanks for listening.